morning, everyone. This is Breaking Ground, so you want to build a C2. Before we kick off, a few quick announcements. As always, I'd like to thank our sponsors, especially our diamond sponsors, LastPass and Palo Alto Networks. Gold sponsors, Intel, Google, Blue Cat. It's their support that makes this event possible. Because we are being streamed live, please turn off your cell phones. We do not have audience mics in this room, so raise your hand high after the talk, and we will call on you. And lastly, just a reminder, photo policy does not allow taking photos of other attendees, and masks should be kept on at all times. With that, please welcome IDigitalFlame.
Good morning, everybody, or afternoon as it feels like to me, honestly. Welcome. So you want to build a C2. So I'm going to talk about some crazy stuff that went through me building a C2 that is fully in use today, kind of actually in the current CTF that's literally running right next door to us. Okay, cool. So give a little bit of background on myself. Obviously, I'm a security guy. I love to program. I love Linux a lot. I love Windows, really, because I've been forced a lot of my life to work on it. I'm a creator of too many projects to count. And at my day job, I kind of do more so security architecture stuff, some offensive purple teaming things. And I do a lot of work for Pros v. Joes. So mainly I do a lot of work with the red team, as you can see. But also I do a lot of work with the gold team, maintaining infrastructure and architecture and kind of doing systems administration stuff there. So, stupid beginnings. As they say, every project starts with a stupid idea. So, we're going to take us back to 2011, the dark ages of Java. A long time ago, when I started college, I was learning Java as one of the programming languages, in my stack that I know today. And they say kind of laziness breeds innovation. I kind of feel like it more breeds stupidity, at least myself. Me being me, I was really lazy and I wanted to encrypt data at rest. And I looked at the implementation of AES in Java and I said, no, screw that. I don't want to do that. That's too much. So, you know what I did? I did the best thing possible. I rolled my own crypto. Don't do that. It led to the invention of CBK, which is a sort of lazy man's encryption. It stands for cipher block key. It's like some round cipher thing. It's probably super duper insecure. But I still list it on GitHub. So, kind of going forward now, now it's like 2017. I started learning Golang because my work kind of wanted me to develop some projects that were kind of architecture and OS independent. So the language at the time really to learn was Go. And I was like, awesome. So me being myself, a person who kind of learns by doing, I really needed a project to learn. I needed something to do outside of my job, like kind of the things I needed to do, because I wanted to dive into the actual stuff that Go kind of provides. So what I did is I revisited some old projects to rewrite. I ended up actually looking to CBK to rewrite. I was like, can I make this crap code run faster? Completely forgetting it's super insecure. So we'll get to where that comes in. But so at the time, currently, I was doing a lot of red team development as well. As most of my life in cybersecurity, I was doing basically offensive stuff. Now, the thing is while doing all this, I never really found a tool that worked correctly, that really fit the needs that I wanted. There was things that were missing, there were workarounds you had to do, and they were super clunky. Things could be dependency heavy, or the setup was super annoying. So that actually led me to a lot of the tools that I've built today. There's some super C2-ish things that I've made, like WSBind. There's some exploits and things I developed. Some of the things I've already previously talked on, like In Your Mems, which is a talk on antivirus evasion. I've also made some utilities, and I've also made some stuff kind of for trolling and shits and giggles realistically. So that all leads to XMT. XMT stands for the Extensible Malware Toolkit. So you might be asking, what is XMT? XMT is an offensive security framework. It does a lot of malicious things really well. And when I say malicious things, I mean anything the MITRE ATT&CK framework may cover, DLL injection, assembly injection, process doppelganging, etc. And it provides C2 functionality. And the only thing that's missing from that C2 functionality, honestly, is a user interface. And what I mean by that is there's no button I can click to say do this. I'd have to script all that out, but everything else is still there. The one cool thing that I made this with, an idea with, is that it can be extended for any purpose. So I leave a lot of room for users to input functions, to change how it works, to add things, to extend functionality. There's pretty much like anything you can extend it to, like anything that really you can put your mind to in code. The one good thing about it, since it's Go, it's multi-platform, multi-operating system, so I've actually took some time to make sure that it supports and it works on every operating system and every OS that Golang currently supports in mainline. But, however, it's currently Windows favored, so meaning like a lot of the toys and the cool things in Windows that it does support really only work on Windows at the moment. I'm adding some Linux support as I go, but some of those are kind of hard to do one-to-one. And currently on the picture on the right, well, it's on kind of my right, that's the status of the repo as it is right now. And currently we're at 32,000 lines as we speak. So what did I want in XMT when I was developing it? I kind of want it to be easy to use. I want it to be modular, flexible. I want it to be simple at the same time. So I wanted something to be, configurable to an extent where it works out the box, but also I could, kind of change up how it works. I wanted things to be not dependency heavy, so I didn't have to rely on a lot of things. And I also wanted to have a small build footprint. I shouldn't have to spend time building my implants. I should spend more time like popping boxes and throwing shells. So, kind of giving a quick list of the things that make up XMT. I know it's a lot. We have the overlying C2 package, which contains like most of the C2 functions. Config, transform, and wrapper, we will actually talk about in the next slides. There is also the task package, which doesn't really make a super big appearance, but it basically handles everything when it comes to tasking or if you want to create custom tasks for XMT to do. Then you have the CMD library, which contains everything executable, so like literally anything, DSLs, assembly, etc. The filter library, the subpackage filter, under it contains the cool filter struct that we can use to literally select processes that we want to target. So we can set parent processes or processes that own our like assembly or a DLL, etc. And we have like cool things like setting the parent, setting if it's like executable, it's in a session or it's a service, excluded processes, etc. Then we have our communications library, which contains most of our communication primitives. The limits library puts guardrails around some of the things we can do, which is kind of cool. Then we have the pipe package, which is actually it's before the Golang implemented named pipes in its standard library, but this actually supports Linux and Windows, and it supports setting security permissions on your pipes as well, so you can do a lot of more cool things with it. WC2 is my own version of a web C2 or basically connections over HTTP, and we'll actually get into that as well. Data is just a package that allows us to write data primitives, so like any Golang primitive. It contains some like cool, really util helper functions, including some like memory buffers and such. Crypto, same, it's just some more cryptographic operation things. Device is actually one of the coolest packages and one of the largest. It contains basically everything from interfacing directly with the device we're on. So we have the evade package, which does like defense evasion, some other things like overriding hooks that might be placed in us by antivirus. We have a local package that deals with identifying and detecting things on the local host. We have the regedit package, which is a high-level interface for the Windows registry. Then we have WinAPI, the WinAPI registry, and WinAPI service. WinAPI is actually my own rewrite of the Windows or the standard library Windows package for Golang, and we'll talk about that one. The registry package under it is the same thing. It's my rewrite of the Golang registry package, and the service is also, again, a rewrite. Man is the home of Guardian and Sentinel. Sentinel is a loader for XMT and allows you to basically load it into like any process based on your rule settings, like load it from like a HTTP endpoint, from a DLL, from a file on disk, whatever. Guardian allows you to keep a singleton instance running currently on the device, and it will keep that instance regardless of what persistent mechanism you use, so you're not like actually running 1,000 implants on a host. Lastly, you have util. It's just like a basic utilities directory, contains some things. We'll get into Xerror because it's a custom implementation of the errors package at Go. It does some really cool stuff that we'll get into. BugTrack is just a debugging library that allows you to kind of log, if a process crashes or anything. Super helpful. Text also contains a regex-free text matching algorithm and basically parser, so you can do like some really cool textual expressions without all the bloat that the regex package in Golang provides. Lastly, we have crypt, and I will talk about crypt in a little bit. It's a sort of textual cryptographic helper that we'll get into that allows you to do defense evasion. So I know that was a really long thing, but I want to highlight now some of the things that actually, and some of the interesting things that are actually take part into XMT itself. So one of the first things if you're developing a C2 is identification. It's like one of the most important things. Basically, it's the process of getting to know our host device. So it might be like the OS version, the architecture, the interfaces, and IP addresses it may have. Then also is basically generating unique identifiers that are unique to that host specifically, as well as any environment info. So like the username, the domain it may be running under if it's Windows, and like your basic process and parent process ID values, for example. And what this actually led me to is we ended up having to create our own UID library. We originally used the machine ID library, but it seems it's abandoned now since like 2019 and unmaintained. So we created our own, which actually used some a little bit cooler features and used a better identification system in Windows, such as using the system SID instead of like the cryptographic hash of Windows, which doesn't change as much compared and is actually a little bit more unique. And that actually led us to generating a 32-byte identifier, which generates a 32-byte machine-specific ID called the signature and a 3-bit instance-specific called just the device session ID. And basically these 32 bytes generate this session ID that's unique across every single host that you connect to. So, networking, speaking computer. Now, developing this, I wanted to be super protocol agnostic, and honestly, the lazy man in me really didn't want to write code for like different types of connections. I wouldn't be able to handle pretty much anything without having to worry about what the underlying connection is. I didn't want to have to, write workarounds for something stupid. And I also wanted to make complex connections, well, easy. I didn't want to I wanted to have complex connections, but I didn't want myself or like anybody else on the other end to have to deal with all the bull crap of like managing that connection. Like, I don't want to have to anybody deal with that. And what I ended up doing is these things now basically operate on the net.con interface, which is just basic to go. So networking. So some of the things that do go into networking, we actually took the idea and split it out into a thing called connectors. And basic connectors are the simple interface that provides the ability to listen and or connect. And it's defined actually in code by two interfaces, which is one, the connector, it accepts a context and a string you want to connect to, and then it returns like a netcon and or an error, and the acceptor interface, which gives you, you provide a context and a bind address, and it returns a net listener and or an error. Some can actually support both. Some are one, some are the other, but most of them do have support for both built in. So, and we have, for built-in current support, we have TCP, UDP, IP, ICMP, HTTP, HTTPS, TLS, MTLS. And like I said before, a lot of things you can create custom ones for this. So the ability for you to create custom ones, you just have to basically implement these interfaces. Then there you go. Okay, so one special highlight I did want to talk about is the UDP connector. So all connectors, at least by default, as you would think, they're stream sockets. So meaning, we're not we're not looking at packets, we're looking at a raw data stream. Now, if you know anything about UDP, UDP is completely packet-based. Same with IP and ICMP, for example. And we really needed a way to support streaming over UDP. I really didn't want to have to deal with UDP on its own separate thing. So I ended up working on developing my own custom UDP listener. And what this listener does is it contains its like own connection ring buffer. And what that does is it maintains an active connections map. And this will take new connections and pipe them back to like the accept calls, or if it already has a connection that we are currently mapping, it'll take the data and push it into the current socket buffer that we have. And this makes internal like a heavy use of channels to work on multiple Go routines at the same time. But it actually works up really great, and it's like super rock solid. Like you could talk over this as if you were talking over TCP, and you wouldn't know the difference. I've used this to like send like hundreds of megabytes of data, and it just goes, which is really awesome. And I ended up taking the success of this one and using struct inheritance for the IP ICMP connector. So now you can talk over ping or like any kind of IP-based protocol as well, the same way, and with easy support. So next one, the WC2 connector. The WC2 connector had the same problem as UDP. It's HTTP. I didn't want to restrict just to post. I didn't want to kind of send like 1,000 post requests like every second. That would be really suspicious. So, I'm no stranger to WebSockets, and in fact, I wrote the scoreboard over there, which makes heavy use of WebSockets. So I ain't no stranger to them, but I was like, man, how can we implement these? So I dove down into the code, Golang source code, and it turns out Golang will return some HTTP bodies as read-write if you play nice, but you need really specific conditions. One, you need 101 HTTP, 101 switching connections, response from the server, can't be HTTP2, and the server must hijack that connection. And this is kind of obvious when you think about like WebSockets, like underneath the hood, this is kind of how they operate. But you need to do this all in like a custom way, so that way you can basically jack that connection right out of there. And what happened is we ended up having to use reflect in order to grab this because we need the direct net con, but we can actually index inside the supplied struct, and we can just pull the connection out of there and now just use that as if we're talking of a raw TCP. So some of the other things that I had to implement to like kind of improve in this area is during my offensive security kind of lifetime and some pen tests is that a lot of firewalls would block HTTP connections based on like their cookie state, and basically like if it doesn't recognize it as like a real like web session, because it would basically apply a cookie to that session over the proxy, and if that session came back without that cookie, it'd be like, no, I ain't accepting you. So I had to make sure that we actually like worked on keeping session state inside as well. And the other thing is we had to add actually proxy support for it. Golang doesn't have any Windows proxy support at all. It has like Nix proxy support, super easy. It's all environment variable based. So what we ended up doing is ended up implementing our own proxy function, and we call it device.proxy. And it's literally a one-for-one drop-in of the HTTP proxy from environment function, which is great. So now we can use this for Linux and/or Windows, and it'll just work out the box. And this uses the WinAPI call WinHTTP get default proxy configuration, which is basically it returns the either system-based or GPO-based proxy config on the host, and we can parse out that data and then get like any of the proxy, like what the HTTP proxy or HTTP exceptions, etc. And we just pull it out and now use it. Now, the funnest thing I like to talk about and the hardest one, routing. Routing is really super complex, and I hate that it is complex. But the reason I made it complex, honestly, is because we need to support like a lot of feature sets. Some of the features we didn't need to support would be like multi-packets. So if I'm sending data to a host or like a command to a host, and that's like one packet, for example, I don't want to have to wait for it to connect back to me again to wait and go send the other one. Like I can just send both of them at the same time. Like if it hasn't talked to me back, why am I going to wait another time to send it another packet? So I can send multiple all at the same time downstream device, so we're not wasting any time. Then we want to also handle fragments. So if the packet's like too big, we want to cut it up into byte slices, for example, because I don't know about you, but sending a 100 meg DNS packet doesn't look okay. Then also there's a mode we created called channeling mode. Channeling mode basically allows you to break the normal like kind of wait back for a packet response from the client or the implant, and now you can act as if you're directly at the terminal of the machine. So it's like instantaneous feedback or instantaneous file uploads, downloads, etc. So we also need to kind of have a workaround for that, make sure that works correctly. And last thing, proxy connections or pivoting, if you're familiar with that nomenclature, where we wanted to be able to piggyback off of other implants connections. And this kind of led us down this huge rabbit hole of basically working on the thing of routing via identity and flags. So to kind of give a button to that, basically we use a struct called packet, which is the huge basis of inter-device communication, and it contains a thing called flags and a device ID. Basically flags are a Boolean state of a packet as it flows through the network to the actual final C2 server. And it notates the fragment size, the fragment state as well. So meaning like the group ID, because we can wait on multiple fragments if we want to, and then the fragment position inside that group, and then the total amount of frags we actually want to receive. Also, these flags will actually determine how we want to act on a packet, as we can like optimize our receiving of packets. Like if every packet coming to us just goes to us, we can just multi-batch process those immediately, versus like if it's a flag multi-packet, meaning that we have to now unpack it, scrutinize, and look to see if we have to forward it to like a downstream client or upstream. So we can kind of use these to like speed up some of our processes as well. So getting into channels that I talked about earlier. So like I said, channels are a direct connection to the C2 server. Like I said, the easy way to describe it, it's like you're at the terminal of that machine. It's instantaneous communication. It will work through proxies and pivots directly as well. Now, the caveat of this is that every single hop between the implant and the C2 server, it enables channeling mode through and through. Because, I mean, obviously, if I'm waiting on a upstream packet from another device, it's not instantaneous anymore, right? So it's going to enable it upstream through every single device. So if whatever end sends the flag channel, it'll then bam, instant set that up, and then once whatever side's like, all right, I'm done, it just sends flag channel end, and the whole thing comes down. However, if one of the hops between like A and B is channeling on its own, meaning like that device specifically has decided it's going to channel, that one stays up unless that device is like, all right, I'm done as well. So that way we're not tearing down other people's connections. So proxying. Implants can piggyback on another implant, meaning like I can talk to another one behind, if I'm like segmented behind a firewall or something. The implants don't need to know at all. So like they don't even know they're talking to a proxy. They think they're talking to the C2, which is great. We don't have to handle it like any different. And we can use a thing called packet tags to mark ownership. And the reason we do this is so we can know where to route packets through. We want to have packet routing like super easy. So we use a thing called packet tags, which are hashes of the device ID, which the server will tap onto its packets. That way there's no extra packets being like added, so we're using less network traffic. And now we can constantly update the server, say, hey, yeah, I still got this guy, I still got this guy, I still got this guy. So the server still knows. Now, what this allows us to do is if we have multiple instances inside of a network and there's an instance way down there deep in the net, it can talk to multiple different hosts. It can keep switching back and forth, and the server on the other end still knows where it's at and knows how to route its packets. So nothing gets dropped, nothing gets missed. We can send them all correctly. So getting into some of the things that actually make networking really fun, at least for me as a red teamer, there's a concept called wrappers and transforms, and they allow you to augment the C2 connection. And basically what this means, it allows you to like obfuscate, masquerade, or encrypt your connection. We have wrappers, which literally wrap the connection. They are stream-based things. They have unlimited uses, and they have an order, so you can go like, encryption, compression, obfuscation, or you can go encryption, compression if you want to. Then we have transforms. Transforms actually transform the connection. They are block-based. They access the entire binary payload before it actually gets written to the wire. So what this means is you can completely rewrite your data. So you can reverse it if you want. You can change it into a DNS packet. You can change it to an image. Doesn't matter. You can do whatever you want with it. But because of how they work, they can only be used once. So some of the things we do have built-in support for wrappers, for example, are encryption. We have XOR, AES, CBK, because I'm funny. We have compression, gzip and LZO currently. We have hex and base64 for encoding. Then transforms, right now we just have base64 and we have DNS. So for the DNS one, I really like that one because it literally masquerades as a perfect RFC fitting packet. So like Wireshark and everything else is none the wiser. That's a DNS like communication between the two. So these will like masquerade right through like a level 7 firewall or layer 7 firewall. So now you may be wondering, all this stuff's going on between like hosts. Well, like, am I wondering about like privacy or encryption or anything? Well, yeah, I answered that with key swapping. So key swapping is a thing that's enabled by default. You can disable it by a build tag. And it's basically a lazy mutual authentication between host A and the server and the implant. And basically what happens is when the implant talks to the server for the first time, it will tag its packet with a specific flag. It's opt-in, but if it's built with it, it always opts in. And then it sends some randomized key material at the end of it. And what it'll do is it sends it to the server. The server will then do some math based on the identifier of the packet and some time-based stuff and the mutual like data that the packet has been sent with. Then the client on the other side will do the exact same mathematic formula, and basically now they have both generated key material or a key that neither side has sent across the network. So now they both have a separate key that they can use to encrypt their packet data without anybody else in between knowing it. Now, because of the fact that we use like the IDs and the flags for routing, we can only encrypt the actual contents of the packet. So the actual data contents of it are encrypted using XOR for speed. but like everything else, like the flags and stuff, aren't really encrypted because we can't really do that. But the cool thing about it is that if I'm sending packets through a proxy, the proxy can't read my packet data. Like it has no idea what I'm sending. It just looks like a bunch of gibberish. But the server on the other end will read it and be like, oh cool, I know what this is. And it's rotated regularly. So every so often, there's a chance that the client will say, hey, server, let's do this again. And the client will send some more key material back to the server, and they'll do the whole song and dance as the beginning. So now, the kind of thing that wraps all this stuff together, profiles. These things bring implant settings together with a little bit of twists. They are a binary table that are kind of like a type length value format, but they can also be in JSON. If you want to be like stealthier and smaller in your binary size, you can actually disable JSON parsing. But it contains settings for containers, wrappers, and transforms. Excuse me. And it contains multiple C2 servers. So if you have multiple hosts that you want it to connect to, it'll just select one and send it to. But they can also contain things called selectors and groups, which I'm going to talk about in the next slide. Selectors and groups. They are one of the coolest things, in my opinion. They can basically break up a profile into multiple like separate like sub-profiles. And what this allows the implant to do is it changes its encryption, or like it changes how it acts on the wire. So like its encryption, who it's talking to, how it acts, it can completely change that up. And that's without any interactions from the person like operating it. Like this will do it automatically. So, you know, it'll switch it up like either, you know, based on like a time or based on randomization. And if the server is configured on the other end to accept this still, then it just keeps going like nothing happened. And basically we use selectors to kind of determine how we switch these. Then we have like last valid, which says, hey, if the first one hits an error, switch to the next one, or random, just as mad chaos, just switch to one like every single time. Or we have round robin, which is every connection operation switch to the next one on a weighted based order. Semi-round robin, same thing, but if there's a 25% chance is hit, then switch, 75% chance, don't. Semi-random is, again, if you hit a 25% chance, then it will switch to the next profile. But it's completely optional. And the great thing about it, though, is we have a Python script in the repo under tools at config.py that will actually like do all this for you. It can either be used as an API directly in Python, or it can be used as like a command line thing, but it allows you to build these like complex profiles pretty easily. Now, defense and stealth. So one of the things I spent a lot of time on for defense is limiting identification. So we basically want to reduce the possibility that when a blue teamer looks at this binary and says, oh, obviously that's a Go binary, or oh, obviously that's, whatever, it's C2, it's malware, etc. One of the things I do this by is reducing the recognizable strings that do exist in the binary, and this actually reduces our size, which to be a plus. We also do some things like some checks and some kind of workaround to look not as malicious as we normally would. One of the ways we do this is we enable a thing called implant mode, which is enabled by a build tag. It basically trims a bunch of unnecessary stuff off the binary, and even though it's Golang and Golang's compiler is supposed to be really good at like trimming the fat on things that aren't used, it can sometimes leave things in there that it may use that are really never actually needed. So we actually basically force it to remove these things completely from the binary. It also converts errors to numbers, so that xerrors package I was talking about. On the wire and in memory, those are converted to a numeric version of the string. So basically, like in memory and everything, they are numbers, but like as the operator reporting back on the error, you would only see the string. So like it converts it back for you. So that's the great thing about it, is that if somebody's doing like memory forensics on it and for some reason you hit an error and it's like access denied, or I don't know, you cannot spawn this process for X reason, it doesn't literally say that. It's just like 256 or something, so, and it's great. It saves us bytes over the wire, and it's kind of less work for us to kind of do comparison. And it also actually guts 3 megabytes of size for the binary, which is pretty crazy. And it also cuts logging. I don't expect an implant to log anything to stud out, so it shouldn't even be printing anything to stud out. Why would you have it do that? But yeah, it cuts it really small, and it removes a lot of stuff. Now, crypt mode. Crypt mode is a really cool mode. It, like implant mode, is a build tag, and it's based on the util crypt library. Now, this actually is a way to compile in all of our strings as encoded, and this removes 90% of our strings from the binary. And I mean R, not like the runtime strings, but like whatever we use, like built-in file paths for like Linux, for example. and it's based on like an LD flags argument that like packs a string table. And you don't have to do this by hand. I think you'd be crazy to do that. We have automated scripts that'll do this for you, and they're included in the tools directory. And what it does is it actually looks at your build tags and your build environment, and it will say, hey, are you building this for Windows? Okay, nix all the Linux strings. We don't need them. Or, oh, you're building for Linux? We don't need the Linux, or we don't need the Windows strings. So it only uses exactly what you're needing. But basically, technically speaking, what it does is it builds a base64 encoded string block. And what that block is, when the program is first initted, it unpacks that block, which is also encrypted with XOR. And on first runtime, it basically slots all those strings into an index on a string table, and all the packages that have consumers for that will then basically load that string via index. So then all those strings will come back into where they are like in their format. So now, defense. I'll build my own loader. So I actually thought the sys Windows package in Golang was really heavy. And what I mean by that is it pulls out a lot of dependencies. It's super string heavy, it adds a lot to your binary size, and honestly, one of my things, it's a pain to deal with. So I said, screw it, I'll build my own. What I ended up doing is it's almost the same-ish, but I added a lot of optimizations to it, especially some like memory specific optimizations, and I also added some mutex locking and improvements as well, so we're spending less runtime like spinning on certain things that we really don't need to. But one of the other reasons I really did it is because I wanted to load DLL functions based on an FNV hash of their name instead of the actual function name. So if you're not familiar, when you load a function in Windows, you first load the DLL by the name, like kernel32DLL, then you load the function name, so like get Windows version, for example. Then you load that, so that's a string value. So I didn't want to do that. I wanted to load it by like, I don't know, 1, 2, 3, 4, 5, 6, and I wanted to load that. So what I ended up doing is I built my own DLL loader that actually basically loaded these like this. And how it works is when you receive a handle to a DLL, it's actually the address that it sits in memory in Windows. So what you can do is you can go to that mapped memory and start just reading it out raw. So what we did is we started parsing and loading the virtual exports table, which contains like all the like an index array of all the functions, and we hashed the string names of them. Then we compare the string name or the string hash to what we had, and then if so that matches, then we look up the ordinal position, match that to the function address, and bam, there's your function. We only have to do this once per DLL it's loaded, so we just load all the functions that we need, then bam, we're done. Now, the only pain in the ass that I had to deal with this is exported functions. So exported functions, if you're not familiar, is when a DLL points to another DLL and another process, hey, that function, it's over there. Now, Windows does this for you automatically, so you would never know it exists, but in this case, it doesn't do it. So it's basically a string instead of a function pointer. So we actually had to parse the string, do load library, then get proc by name in order to actually grab that. But now we had it automatically, and that's it, works perfectly. And as you can see on the code on the right-hand side, that's actually literally the code that we use for this. It looks weird, I know, because we're doing a lot of memory operations, but like, for example, at the for loop, the 3 lines after, we're getting the FNV hash of the string. We're just like casting the string value to a 256 byte like array, so we can just grab it from there. Then we just grab the address of the function after that, then we check if we need it. Then we just check if it's an exported function, and if it is, we go do that, resolve that. If it's not, we just store it, and that's it. It's actually pretty simple once you kind of get around to it. So, and as you can see from the left and the right-hand side, so on the left-hand side is what we had before when we had all of our functions loaded by string value. And on the right side, we have our functions now loaded as their FNV hash value. So now, none of these string values will now be in our binary at all. Which is actually really cool. So now we can like load like dangerous function 1, and you know, you can strings for dangerous function 1, it doesn't show up. So I kind of went over a lot of like highlights of things that are like, there's a lot of things in XMT that I kind of wanted to go over, but like I don't have a lot of time, so I wanted to make sure I at least cover the highlights of it. But you know, what I did want to share as well are some of the things that kind of maybe really mashed my head into the desk when I was building this. There was a lot of those moments, honestly. But yeah, I kind of wanted to cover some of the funnier ones. So, killing the unkillable. This was a really fun one. So, the Golang runtime was never meant to be killed. It was never meant to be like ended at all. So like if you go search for like closing the Go runtime on like Google, you get a bunch of Stack Overflow results and people are like, well, how can I close the runtime? And they're like, good luck, buddy. Like there is no way to do it. The devs have even acknowledged the fact there's like no way to do it. Like I've looked in the code myself. You can't shut down the runtime. So imagine you had your own library, legitimate thing, like it's like legit library.dll. You load it into a process. Then you're like, all right, I'm done. You exit, close all the proper functions, do all like the niceties that Windows wants you to do when you're unloading a DLL. Cool. Go back and look at that process in like Task Explorer, Process Explorer. You'll notice the runtime's still just chilling there. It didn't quit. And you know, it might be, oh, this is fine, but like when you're injecting into LSASS, this ain't good. So you wanna you wanna get rid of this in some way, shape, or form. So I actually found a way to do this, and it's, in my opinion, really clever. We found a way to kind of clean up all of the Go routine functions and Go routine threads that are going on. So Go actually doesn't keep track of its threads that it creates. It doesn't. Like you go look at the code, it doesn't care. It creates a thread, closes the handle, all right, whatever. So I was like, crap, well, how do I do this? I can edit the runtime, which I can do that. I've done it. I tweeted about it actually. It's just like, I want to add this, but I know nobody's going to accept that commit. So I was like, okay, well, I got to find another way. So I put on my blue teamer hat and I said, all right, well, how am I going to find a Golang thread inside a process? So what I ended up doing is you can actually, all the Golang threads have the same base start address. All of them. They literally do. So if you look in the, at least for Windows, I can say this. If you look in the code, then you search for like create thread A. You go down, it's the same function. So it's the same function address every single time. And you can verify this by going into the Process Explorer and looking at the threads. Same base thread address. So I said, okay, cool. Same base thread address. And the other thing is they're all started roughly around the same time. Cool. So we can identify those. So we say, all right, now we enumerate through our threads. We say, okay, is it in the same module as us? Yes. Cool. Same base address. Cool. Is it started around the same time? Cool. All right. Kill it. There you go. And then we just kill our own process. Go runtime's gone. So I run this now, and if you run this and you look at the thread, runtime's cleaned. So, and this actually led to the development of device.goexit, which eventually does call WinAPI kill runtime. I'm trying to work on this for Linux. It's a little bit harder, in my opinion, because I have less Linux development experience. But on Windows, you can just call kill runtime or goexit, and it'll just completely clean the Go runtime. And in fact, I did a commit literally a couple days ago to fix a bug. It was so good at killing the Go runtime that if you had two runtimes loaded in a process completely for different reasons, like you had a Golang service running in a thing, and then you had an injected DLL, and then you injected assembly. If you ran this, it killed everything, which not good. So I actually edited some fixes that actually make it only kill itself. So I thought that was kind of an interesting way. So now we can actually kill the Go runtime. Second one, crashing with style. So I actually had a problem that I actually blue screened a lot of boxes during a CTF one time. And I really didn't know why, and I ended up blue screening a lot of my testing boxes too, and I couldn't figure out what the hell was going on. So, and basically I kind of narrowed the actual cause down to CFG, which is Control Flow Guard in Windows. And this runs for pretty much every operating system based binary, so like scope host, or I don't know, kernel, LSASS, etc. And basically strict handle checks are a thing. What that does is if you operate on a valid handle, doesn't matter what you do, it kills your process immediately. And so if you call close handle on an invalid, handle, it still kills your process, which is like, dude, I'm just trying to close a handle, which actually ended up being the reason why my process was crashing, by the way. And what was causing it was there's a race condition in the CMD process struct that the process opened, closed way too quickly in the span of CPU time. So my Go routine that started to watch it didn't start in time enough for that process to close. Then wait for single objects, for some reason not documented, by the way, in the API documentation for Windows. It will wait infinitely for the process to end, or for the process now, because it's dead. So wait for single object just waits infinitely. So trying to close that you would call close handle on it, and that would cause the crash. So now you would see a blue screen on your device. And Windows wouldn't log this. I couldn't get it to log it. Seriously, there's nothing I could enable. Like even syslog doesn't log this. So like I was like, okay, well maybe I'm doing something weird with memory because I've so done that before, but no. And I kind of narrowed it down to this. So I ended up having to call wait for multiple objects, which works properly, and we create our own event as well. So we now have our own event to signal, so that way we can actually end it properly and detect that invalid handle if it happens. Last story time I have, process dump woes. So the WhenAPI function mini dump write dump is really weird. It's really weird. In-memory handle pipes behave oddly. So I actually, I was using this to write a thing because now you can dump process, it allows you to have a native function to dump process memory. And I was like, all right, let's just dump process memory to see if it works. When you use it it allows you to specify a file handle. So when you specify like an in-memory file handle, like a memory pipe, for example, it dumps, it works. It drops 40 bytes off the response, just for no reason. I can't figure it out. If anybody knows, let me know, seriously. But like that memory pipe completes, 40 bytes are gone, and it just those bytes are important to the backup, and it basically invalidates it completely, which is great. So direct dump worked fine, so I was like, huh. So I ended up having to work using callback functions, which I actually found out about Sliver, and I was like, oh, cool, let me take a look at what they're doing, because they implemented that as well. And they had a great example of like using that, and I was like, all right, so like I have to do it this way apparently, which is fun. But yeah, so I had to basically do the long way just to kind of get this to work. So, demos. So I have some cool demos here. Oops, wrong button. So I'm going to do the second demo first because my internet connection is really bad in this room. So I apologize for that. So, okay, so this is actually one of the real implementations of XMT, like as a proper C2. It's called Thunderstorm. So Thunderstorm has things called bolts, which are implants, and this C2 is actually what we're using over there. So so currently there's nothing here, so I'm going to go back into my Windows VM, and as you can see here, there's a little exe. It doesn't look harmless, or it looks harmless. Test exe. So I'm going to run it. I don't know why it didn't pop up. It's supposed to pop up. But as you can see now, it shows we got a bolt here. So we're like, cool. So we can actually go into it. So type it in. And we now got an interactive shell. Is that legible in the back? I hope. So we can actually type in like net user. And it'll just take a sec. And then now the bolt has told us that we accept the job. And most of this is built into XMT. It's just literally the pretty front end is like the only thing that's added onto this. So now we just got our output from our command. And for an example, I can run channeling mode that I talked about earlier. So I do a channeling mode and it says, okay. So, and there you go. So now we have we sort of have like direct interaction with it. We don't have to wait, as you notice. There's no wait period at all for it. So we just keep entering commands, and there you go. So what we're going to do is we're going to do some other fun things. So now one cool thing is, as we can tell, we go into here and type T, and we see test exe sitting here looking all nice in our process list. So let's change that. So let's do a migrate. So we do migrate, target, explorer, exe, method, ASM, and then we're going to point to a DLL. Let's test. Let me make sure I have it. Test with D on DLL. So we're going to hit enter. Oop. Can't spell. There you go. Okay, so now we did a migration. So if we look, now our process ID is 3988. I don't believe that was our one before. So we go back, it's gone. So we go to 3988. So now we're running in our Explorer process. So now we completely switched context between process 1 and process 2. And we're still running. We haven't switched, we haven't lost any context or anything. We're still in channeling mode, running perfectly fine. So our network connection switched over to Explorer EXE, and basically everything else that we had, the knowledge base, if you will, switched over. And this is still native to XMT. This is not like any pretty add-on that I've extended or anything. This is all default context. So let's do something. See, I can also do some other things like looking at Windows, so I can see what Windows are on their machine. There's a lot of like capabilities we built in, like some really stupid, pretty stuff for Windows, as you can see. But those are some of the examples. And let me see if I can get my Wi-Fi working. I will show you the live thing. Because currently we have the live CTF running. The reception in this room is really bad. All right, we'll worry about that later. So I can't show that demo because it's really bad connectivity. No, I'm not gonna go about that. It's really bad connectivity, and I think it's not playing nice. But these are some resources that I have. So we have the GitHub repository. It's just dig.sh/xmt. That's the direct thing. All the code for this, by the way, is public. I don't close source anything. I don't believe in closed source code. So if you want to fork it or use it, I don't care. Also, Thunderstorm, the thing I was using, also all open source as well. So if you ever want to use it, just for shits and giggles, or you want to poke at it to see how it works, go for it. It's at dig.sh/ts. And lastly, there's some other things that I looked at that really helped me kind of get like a better handle on some things. And there was a really great talk that resonated with me, which was during DEF CON Safe Mode. There was a talk by Ben Kurtz, and it was Offensive Golang Bonanza. If you haven't seen it, it's a really good talk. I really love his talk. So yeah, we have about like 15 minutes. I can close up. Thank you guys for listening to me rant for a little bit, and then I will go for questions. If there is any. You over there.
So have you done anything as far as the CPUs to make them look more like actual web traffic, or do you have a way to customize and do that sort of stuff?
Yeah, so he asked if there was any way that I made like CD traffic look like web traffic. Yes. So the WC2 listener, I may not mention it, so it's my fault. WC2 is basically a web HTTP C2, so it looks exactly like standard web traffic, if that's what you mean. It carries like all the default headers. I did want to do like a direct get post one, or one that looked like posting images. That's a connector I'm planning to add. But right now, WC2 is like the go-to for that, so it'll do that, like all the proxy support and all the fun junk. And it will. I'm missing the word here, but that's the one that will do that currently. So there's a lot of options to it that it's more than I can explain in a kind of a talk, I feel like. But if that answers your question.
Sort of, like people don't normally just hit a web page over and over.
Oh, you're asking.
JavaScript.
Gotcha. Oh, you're asking, does the URL change? Yes, right? That's what you're kind of asking? Yeah, so the text library is a text replacement and matcher like algorithm thing. You can supply special text routes that will do that. So you can say like, I want a string route that looks like this, or I want a route that looks like this, so it changes every single call. Is that what you're asking? Yes, we have support for that. So yeah, you just have to write like a regex looking string, and it'll take that and then parse it out as with. And then the endpoint can actually match those, so you can actually kind of catch blue teamers trying to do that. So you can match on like the URL, the header, headers, host names, user agents, etc. So, but yeah, does that answer that?
Yeah, thank you.
Cool. You in the front.
The functionality that you were describing under the profile section that's kind of similar to Cobalt Strike's beacon shell, would that be detectable with tools like beacon analysis that John Moran put out with active countermeasures and things like that?
So you were asking if the C2, the profiles thing would be, since it looks like it looks like the Cobalt Strike's kind of profiles method. I don't think so. If it is, that's really cool. I don't think so because it probably sits in a different memory layout. And for at least, so for Thunderstorm, we actually encrypt all this stuff as well. So it's actually XOR wrapped and everything in memory and after it's used. So I don't think it would fit. I don't think it would check it. But if it does, that's awesome. But just because
traffic analysis, so it would be like the jitter and the thing, it kind of has that built in. So it's based on like
and we do have jitter and stuff, so you may be able to match it on that. He asked if it would, he might be able to match like the jitter or something, which yeah, that could definitely match that, I would say. But I don't think it would match that traffic exactly. If it does, that's pretty awesome. But I don't, because of the layout and everything, I don't think it exactly matches one-to-one. Does that answer your question? Cool.
What advice do you have for blue teamers?
Oh God.
When you're working?
Blue teamers, so blue teamers, one of the things I try to tell blue teamers all the time is know your land. So like know what's running. So I deal with a lot of Windows things and people forget like what is actually like native on Windows. And granted, I don't expect you to know every DLL, but I want you to spot inconsistencies in it. Like there are some, so I can make binaries in Windows that look like exactly like Windows binaries, but there's things you can kind of look at and be like, that's kind of sus right there.
Like what?
Okay, I'll give you one. So a lot of people don't sign with binary manifests. So like examine your binary manifests. I've seen a lot of people compile without them. Like resourcing is becoming more popular. A lot of people don't resource. So if you look at a binary and go to its details tab, that's the resources of the binary. So you can like specify custom like values for its name, title, description, etc. Analyze that first. And if they're smarter, they'll put those in there. But then manifests are a thing people don't catch, like compatibility manifest, Process Hacker too. If you've never used Process Hacker, look at it. I found about it last year because a blue teamer told me about it. It's really awesome. And it can examine manifests and like it'll say if it's manifested for this Windows. Like I'm running Windows 10. Why is this program manifested for Windows 8 saying it's LSAS? I don't know about that. So, like that I would say would be a first start, but also examining like, like I used to love Carbon Black for this, is you can examine your threading and stuff. Like process hollowing is a big deal that a lot of people don't catch. So like examine, like look at like even Process Explorer will be able to show you like, that thread doesn't look right. Like Notepad shouldn't have more than one thread, and Notepad's single threaded, by the way. Like it shouldn't have like multiple threads running in it. Does that kind of like answer? Like, I could probably go on a lot about this.
Yeah.
Like I talk a lot over there. So, but I hope that helps lead us a little bit. Any other questions?
One other.
Yeah, go ahead.
In terms of the loading of your initial payload on a system, do you have any options as far as putting like a PowerShell command that keeps one-off or something like that?
So I want to do that. I don't have a script written up for it. I can do it. So the thing you noticed with migrate, you asked what are some of the things I can use for loading, like in the initial compromise loading, and you were saying about PowerShell loaders. I want to build that. I haven't built that yet, but we can load via assembly. We have there's a built-in, I've built in the SRDI library into XMT, at least the DLL to ASM loader, and so you could convert DLLs to ASM on the fly. And so we do that a lot. So that migrate that we noticed, I did that all in ASM, but the DLL was an actual DLL. But we have that capability. We have that for other things. So like there's a loader we have for Thunderstorm that does that, like natively, but not with PowerShell. It's on the roadmap, I guess, is my answer. Does that answer?
Yeah, just a quick follow-up.
Yeah, go ahead.
Once you have the initial loader stuff on the system, is there a way to
Go ahead.
is there a way from that subloader to kind of I forget it, I'll articulate it better.
Okay, yeah, if you catch me around somewhere, you can ask me, I will talk your ear off. It's okay. Is there any other questions before I close out? Go ahead. Sorry. So he has for key swapping using Diffie-Hellman. No, because I'm too lazy to do that, but I would love to do that. What? Oh, I'm too lazy to do that. I'm just doing like a basic key swap, and I'm basically using the material on both sides to do basically the values only one way, if that makes sense. So like I'm not sending any of the key data like at all. I'm sending the basic source material to generate from that, but it's not any Diffie-Hellman, unfortunately. No. Any other questions? Cool. So thank you guys again for listening. I hope you guys have a great rest of your week and happy